It's good to see all of you again. You guys survived semester 1 of health sciences, so you should be happy about that. And if you're here, I'm guessing you all passed Chem 191, so well done. So BIOC, and thank you to everyone that filled out the feedback. So there was some good feedback, and thank you for that. Definitely take some of that on board. And so BIOC192 is basically about the chemical reactions that go on inside the human body. And in order for those reactions to occur, you need to have proteins. So a lot of it's going to be about learning about proteins, and what makes up proteins are amino acids. So today we're going to be going over amino acids. You're going to be covering them in the lectures this week. So yeah, it's kind of, I'm just covering this week's content just because last week's stuff was all kind of just introductory. There's no actual, it was really general, so there was no nothing specific to go over. So yeah, I'll just get started on all the amino acids. So you should all have a worksheet in front of you. Okay. And I've just made it so that there's some gaps that you can just fill in as we go along. Okay. Okay. So first of all, we'll draw the structure of a generic amino acid. So you probably know this from Chem 191, but you have a central carbon. So your this carbon, you have one carbon in the middle, and that's going to be your alpha carbon, okay? There's your alpha carbon. And then on one side, you're going to have a carboxyl group, okay? So this is, there's a double bonded O and a hydroxyl group on the other side. So that's, this is this part here. This is your carboxyl group, okay? So that's a COH. And then on the other side, you're going to have a nitrogen, and this is your amino group, okay? So if it's neutral, it's going to be connected to 2 hydrogens, okay? So this group here, this is your amino group, okay? And then it's also going to be connected to 1 hydrogen atom, okay? And then, so in every amino acid, these 3 groups are always the same, okay? But what's different is going to be the R group, okay? So this R group could be anything, but this is your, this is the structure of your generic amino acid, okay? All right, so there's 20 different amino acids that make up the proteins in humans. Now, there are more amino acids that exist, but only 20 of them are used in the human body, okay? And so all of them, apart from glycine, they are chiral molecules, okay? So if they're chiral, it means there can be an L form and a D form, okay? And the reason that glycine, I'll go over this later, so don't worry about that. So amino acids, they can have a 3-letter and a single-letter abbreviation. Okay, so you don't have to remember the abbreviations, okay? Just be aware that they have those abbreviations, okay? And so in solution, if they're in an aqueous solution, most of your amino acids aren't going to exist in this form. they're going to exist in a form called a Tute ion, okay? And what that is so if you have it in solution, remember that this carboxylic acid, it wants to get rid of the proton. Okay, so it wants to get rid of this hydrogen proton, H plus ion. So this one's going to come off. And so this carboxyl group is going to become negatively charged. And you'll have an H plus that's come off the carboxyl group. And this group here is going to pick up an extra hydrogen because it's an amino group, okay? And this group here, this amino group is going to be positively charged, okay? So this is the Tute ion form of a amino acid, okay? So you can see that overall, the net charge on this particle, on this amino acid, is going to be neutral, okay? But it's made up of one positive charge and one negative charge. Right. So then, depending on what this R group is, that's going to determine the property of this amino acid. Okay. So our first group that we'll look at is the nonpolar amino acids. Okay. So if it's a nonpolar amino acid, this R group is not going to contain an oxygen atom. Okay. So the R group doesn't contain an oxygen atom. And the reason for that is that oxygen atoms are very electronegative, so they'll pull electrons towards themselves. And then so that means that oxygen atoms will have a net, a partial negative charge. And that means that it's going to make it polar, right? If you have a partial negative or positive charge, that's going to make you polar. So the R group will not contain an oxygen atom if it's a nonpolar amino acid. Okay. And if you're nonpolar, are you going to be hydrophobic or hydrophilic? If you're nonpolar, right? Yeah, hydrophobic. Okay. So if you're nonpolar, you're not going to want to be around water because water is a polar molecule. Okay, so polar goes with polar and nonpolar goes with nonpolar. So it's a bit of a chemistry revision right now. And that's an important concept to remember, okay? So nonpolar amino acids are hydrophobic. And if they're hydrophobic, if you have a big protein, so you have a protein that's all wrapped around like this, and remember that this will be one amino acid, there'll be a second amino acid, third, fourth. So this is just a big long chain of amino acids put together. That's what a protein is, okay? So you've got this long chain of amino acids. So if you have a nonpolar, if this protein is sitting inside an aqueous solution, so it's sitting inside water, the surface is going to be water, so it's going to want to get away from water. So that's what it means, hydrophobic. So it wants to get away from water. So that means it's going to be inside the hydrophobic core of the protein. So nonpolar amino acids are usually found in the hydrophobic core of proteins. Okay, so you've got 3, 4, 5, 6, 7. You've got 10 nonpolar amino acids. Okay, and so in the exam, in a multi-choice question, they might give you a picture of an amino acid, and they might say, what is true for this amino acid. So they'll say this option A, this amino acid is hydrophobic. And if it doesn't contain an oxygen atom in the side chain, then you know that that's true. Or they might say this amino acid would usually be found in the hydrophobic core of a protein. So then you know that would be true as well, okay? So then I'm going to go through 3 examples of nonpolar amino acids that are a little bit special, okay? And they usually ask things about these amino acids specifically in these multi-choice questions, okay? So your first one is glycine. This is a nonpolar amino acid, and in this case, the R group is just a hydrogen atom, okay? So if the R group is a hydrogen atom, this means that it's a glycine, and it's an achiral amino acid, okay? So remember that if there's 2 groups that are the same, you can't have chirality, okay? And this amino acid here, glycine, is commonly found in turns and loops. So we'll go over this more later, but in a protein, at the end, it's going to turn around like this, and this is called a turn, okay? If there's a sharp bend, that's called a turn. And because this hydrogen atom is very small, it allows lots of flexibility in the bonding, okay? And then we have proline. So proline's a special one because it's the only side chain that is actually connected to the alpha carbon twice, okay? So you can see there that our R group it's actually connected to our amino group, So it's actually connected to the amino group, okay? So because it's connected, the side chain is connected to the amino acid in 2 places, this makes it quite rigid and doesn't give it a lot of flexibility, unlike glycine, which I said was very flexible. But because of this, it's always going to be at a certain kink, all right? And so that's why it's also found in turns and loops. But it's not going to be found in beta sheets or alpha helices, and we'll go over that more next week. Okay. And then and then cysteine. So cysteine has a sulfur atom on it. So the R group for cysteine is a carbon atom, and then this is called a sulfhydryl group. So it's got a sulfur on the end of it. So that's your cysteine. Okay, and so the thing with cysteine is that it can form a covalent bond. So remember that covalent bonds are strong, right? So covalent, co means to share, and valence means like the valence electrons. So they're sharing electrons, which is a much stronger bond than just an ionic bond. Okay, so if you had another, let's say we had another cysteine atom. So here's another, okay, so we've got, okay, so you've got 2 cysteine amino acids close to each other. So oxidation can occur, and then they're going to get rid of their hydrogens, and they're going to form a bond between each other, okay? And that's going to be a covalent bond. And we call that, because there's two sulfur atoms involved, we call this a disulfide bond. Okay, disulfide bond. And that's going to be important in stabilizing the structure of proteins. Okay, and in BIOC192 they classify this cysteine molecule as a nonpolar amino acid, but in some textbooks they might classify it as a polar amino acid because it is slightly polar. Okay, but for BIOC192 you can just regard it as a nonpolar amino acid. Okay. Okay, so now we're going to move on to polar uncharged amino acids. Okay, so if it's polar, it means that the R group will contain an oxygen atom. Okay, and if it's polar, it's going to be hydrophilic. Okay, because water is also polar. And so it's going to be found on the surface of the protein, okay, next to the water. So you've got there's 5 polar uncharged amino acids, and you can see in the R groups, in all the side chains, sorry, I should explain. When I say side chains, I mean the R group. Okay, so side chains and R group means the same thing. Okay, so if you look in all the side chains, they all contain an oxygen atom. Okay, but if you just have so this is your H. So if you have this is called a hydroxyl group. If you have an hydroxyl group, that's going to hold on to its hydrogen atom more tightly than a carboxyl group. Okay, so these ones are usually going to be uncharged, okay, because it's going to hold on to that proton. Okay. And that's why we say they're uncharged polar amino acids, because at a pH, at physiological pH, so this is another word that I'll use. So when I say physiological pH, that's the pH level of your body if you're healthy. So that's about 7.4. Okay. So when I say physiological pH, that means 7.4. So that's the pH of your body when you're healthy. Okay. And then we'll move on to acidic polar amino acids. In this case, the R group contains a carboxyl group. Okay, so remember this is a carboxyl group, the COOH or COO minus. Okay, so you have 2 acidic amino acids, and they are aspartic acid. Okay, so aspartic acid is, you've got CH2, C, you've got okay, so this is the structure of aspartic acid. Okay, and they can also say aspartate. Okay, so aspartic acid is when you have the proton attached, and it's aspartate if it's lost the proton and it's negatively charged. Okay, but it doesn't really matter. Okay, you can just say aspartic acid or aspartate. They're both referring to the same thing pretty much, but to be technically accurate, it's aspartic acid if it's protonated, and it's aspartate if it's deprotonated. Okay? All right, and then the other acidic amino acid is going to be glutamic acid. Okay, so this one's got one more carbon in its side chain. Okay, so again, when it's protonated, so it's going to be called glutamic acid, and if it becomes deprotonated, so at physiological pH, it's going to be deprotonated, so it's going to be glutamate. All right, but you can say this is glutamic acid, and it's going to be okay. All right, just be aware that you can say glutamic acid or glutamate. But that makes it pretty easy. Okay, so the only two amino acids that end in ic acid or ate is going to be the acidic ones. Okay, so that's how you can remember that these two are going to be acidic. Okay, and they're going to contain a carboxyl group. Okay, and this one's ending in ic acid because it's a carboxylic acid. Okay, and so the thing here is that it's also going to have another negative charge in its side chain. So it's going to be negatively charged at physiological pH because it's got two negative charges and one positive charge. So it'll have a net negative charge. Okay. Yeah. So for that second bullet point there, it should say the carboxyl group has a low pKa, so it releases a proton in aqueous solutions, hence it's negatively charged at physiological pH. Okay, and it's going to be found on the surfaces of proteins. Okay. So I'll go over the basic amino acids now. There are three basic polar amino acids. So this means that the R group is capable of accepting a proton. So remember that's what a base is. A base is capable of accepting a proton. And it's usually going to be a nitrogen atom that is going to act as the base. So the R group contains at least one nitrogen. But tryptophan, which is a nonpolar amino acid, it also contains nitrogen, but it's not basic. And the nitrogen group usually accepts an extra proton at physiological pH, and so it's going to be positively charged. Okay, so if you had so if you have a positive charge here, a positive charge here, and a negative charge here, there's two positive charges and one negative charge, so it's going to be net positive. And because it's polar, it's going to be found on the surfaces of proteins rather than the inside. Okay, so your three basic amino acids is lysine, arginine, and histidine. Okay, so it's probably worth remembering which ones are the acidic and which ones are the basic amino acids, okay? Or at least be able to recognize them, okay? All right, so then we'll go over what the pKa is. So the pKa is basically just the log pKa equals it's the acid dissociation constant. I can't actually remember like the exact definition of it, but it's related to the Ka, which I'm sure you all covered in Chem 191. But yeah, you don't really have to do any calculations using pKa in BIOC192. You just have to recognize what it is. So remember that if the pKa of a group is low, it's going to be acidic. So if the pKa is low, it means it's acidic. So it will release a proton. And if the pKa is high, it means that it is basic, or you could say alkaline. Oh no, so you can't say alkaline. It's going to accept a proton. Okay? So that's the basic concept that you have to understand. And beyond that, it's not too much more important than that. Okay? So the pKa is specific for an ionizable group. So this group here, the amino group, is ionizable. So this will have a pKa. And usually the pKa of the amino group is about 10. Okay? So usually the pKa of amino group is about 10, and the pKa of the carboxyl group is usually about 2. Okay, so you can see that the pKa of the carboxyl group is much lower, so it's going to release a proton at physiological pH, while the pKa of the amino group is high, so it's going to be accepting a proton. So going over the bullet points, the pKa is specific for an ionizable group and tells us the pH at which half of the groups will be protonated and the other half of the groups will be deprotonated. If the pH is lower than the pKa of the molecule, then most of the molecules will be protonated. Okay? So remember that if the pH is low, there's more protons around. And if there's more protons around, it means that it's more likely. So in this situation here, let's say that we were in a very acidic environment. So if the pH is very low, there's going to be lots of protons floating around. And so it's more likely to collide with this negatively charged oxygen atom, and it's more likely to become protonated, right? Okay, but if the opposite was true, if the pH is high, that means that there's less protons in solution, so it's more likely to come off, and that means that this ionizable group is more likely to be deprotonated. Okay? And you can also use the Henderson-Hasselbalch equation to calculate the percentage of molecules that will be protonated versus deprotonated at a given pH. But that's not really too important. Okay? And I've put the equation there if you want to look at it more. Okay. And then we'll go over the isoelectric point. So the isoelectric point, which is also called the PI, it's the pH at which an amino acid will be electrically neutral overall. Okay? And so an amino acid exists normally as a Tute ion, and that means it possesses both a positive and a negative charge, but it's going to be neutral overall. And so the Pi is going to be the midway point between the pKa of the two ionizable groups, which is the amino group and the carboxyl group. Okay? So I said that the pKa of this amino group is about 10 for the amino group. So for your standard amino acid, which doesn't have an ionizable group in the side chain, the pKa of the amino acid overall, the Pi, is going to be halfway between 10 and 2. Okay, so the pKa of most, sorry, I keep saying pKa, but I mean Pi, the Pi of most amino acids is about 6. Okay. So that means that at a pH of 6, it's most likely to be electrically neutral. Okay. And so if you have an amino acid without an ionizable side chain, and the pH is lower than the isoelectric point, then the carboxyl group is more likely to be reprotonated, and so then most of the amino acids will be positively charged if it doesn't have an ionizable side chain. Okay. If the pH is higher, that means there's less protons around, and then that means the amino group here is more likely to lose a proton, and so then because they don't have this positive charge anymore, they only have the negative charge, that means they're more likely to be negatively charged. Okay? So that's it for today. It was pretty quick just because you guys haven't covered a lot of content yet. I didn't want to get too far ahead. Okay? But yeah, I'll stick around for a bit if you guys want to ask me any questions. Okay, thank you. All right.
I just have a question about the chiral thing.
Yep.
You said if it's like these ones